Welcome everyone. In this video we are going to derive the formula for finding the energy of a satellite in an orbit. So let me draw the picture for you. Let's say that we have a big mass like this. It is called capital M and it is being orbited by a little case m. It is orbiting the other mass, the heavier mass, in such an orbit, and it is going to be a circular orbit, and this is actually practical because all around the globe there are satellites orbiting the world and transmitting radio waves and all that stuff so that we can watch TV and have other technological instruments functioning basically. Now the distance between their center of masses will be called r. And as I said, we want to find the energy of the satellite. So we want the energy of this little mass. We will be interested in mechanical energy. So the energy is going to be equal to kinetic energy plus the potential energy. Now, in one of my previous videos, I showed that the potential energy in this kind of a case is equal to negative g and multiplications of the masses divided by the distance between their center of masses. And you can access this formula's derivation from the cards right now. So the only question here is just finding K, the kinetic energy. And you might know that kinetic energy is in the form, by definition, it is in the form 1 over 2 mv squared. Now, what I want to do mainly is I want to eliminate this v, which is the speed. I want to substitute for v, or we will substitute for v squared. You will see that it will be easier in that case. But anyways, I want to replace v. I don't want v in my equation. So how can I get rid of it? And to get rid of it, I will consider the forces. I will say that since we are going around a circular orbit, the net force on us will be a centripetal force, F cent, and I write it with a C as a subscript. This should equal, well, what is causing the centripetal force? What is the centripetal force? It is the gravity, the force of gravity. There isn't anything else between these two masses. They can't exert another force on each other, so it is going to be the force of gravity. Now the formula for Fc, and let's call these, let's take their magnitudes. I mean, even if we took the vector form, it wouldn't matter, but taking the magnitudes is much simpler, I think, in this case. So what is the magnitude of the centripetal force? It is, using Newton's second law, which I also derived in a previous video. You can access it from the cards as well. It is m times AC. This is a special case of Newton's second law, but we don't need to get into it in this video. This is m times AC. And what is the force of gravity that Newton gave us? It is g times the masses divided by the distance between them squared. Now, in one of my old videos, I proved that the centripetal force, this AC, is equal to v squared divided by r. So I am going to substitute that. And you can access that video from the cards as well. So we have v squared divided by r is equal to g capital M, small case m, and r squared. Here we see that the m's cancel. This means if we have satellites with different masses in the same orbit with the same radius, they have the same velocity. We also see that one of the r's cancel, and we get that v squared is equal to, and well, actually it is okay. There here just one r cancel, so there is one r left. We get that v squared is equal to gm divided by r. And remember, capital M is the mass of the bigger object, basically the Earth in this case. So the mass of the satellite is not important for the speed calculation. It doesn't affect the speed. Now what we do is we take this and we substitute it here. All right? So let's go. So we have that E, the the total energy, the mechanical energy, is equal to 1 over 2 m, and instead of v squared, I am going to write gm divided by r. Then we have the potential energy, which is negative gm times m divided by r. And to get the same denominator of 2r, I'm going to multiply the top and the bottom in the second term by 2. This doesn't change the value of the expression. And if we combine them under one denominator, we will get g m 2r with a minus sign here. So this formula is the formula that you can use for finding the energy of a satellite in an orbit, basically. Anyways, I hope this video was helpful. If you have any questions, please write them in the comment section. I hope to see you in another video. Until then, take care.